Okay, so we left off with this exercise to do long division. Whoops. So we're going to put the dividend p of x in the little box here. Okay, and we want to divide by 2x squared plus 1. So we take the lead term here, divide by the lead term here, we get 2x squared. We'll multiply overall this whole thing by what's here, so we get, oops, sorry, not 2x squared, but it's x squared. So that we get 2x to the fourth plus x squared. And so notice here, whoops, I'm sorry. Let me put this x squared over here, because when we subtract, we're going to subtract like terms. Okay? So when we subtract here, we get 0 here, and 5x squared minus x squared is 4x squared, and there's also this term that drops down, which is minus 6x cubed. Okay? So this is our new lead term, dividing by this lead term again. If you divide negative 6x cubed by 2x squared, you get minus 3x. So we have minus, again, we multiply this minus 3x overall by the dividend, or sorry, by the divisor. And so we get minus 6x cubed minus 3x. And again here, notice that this minus 3x is not an x squared term. So hence, it's best to actually drop this next term down simultaneously. And now subtract. And say, okay, these guys cancel again to give 0. Here I just have 4x squared, and then I have plus 4x. Okay? Because I have a plus x and a plus 3x overall, so plus 4x. And let me drop down the last term as well, which is the 2. And so here we can divide one more time. So the lead term 4x squared divided by 2x squared just gives you a plus 2. So we have plus 4x squared, and then plus 2. We subtract, and we get 0 here, we get 0 here, but we have a 4x as our remainder. So this thing actually is our remainder. And note that the degree here, the degree of our remainder, is a degree 1 polynomial, x to the first power, and that's smaller than our divisor d of x, which has degree 2, because it's x squared. So once we reach the point where the bottom, what we get here is smaller in degree than the divisor, then we stop. So what we have then is p of x is 2x to the fourth minus 6x cubed plus 5x squared plus x plus 2. D of x is 2x squared plus 1. Q of x, our quotient, is x squared minus 3x plus 2. And our remainder, r of x, is 4x. And you can write this, I'll just write the forms again. You can write it all out. So p of x, the overall, in terms of the division algorithm, p of x is equal to d of x, q of x, plus r of x. Or you could write the solution as p of x divided by d of x is equal to q of x plus r of x over d of x. And you can, I'll leave you guys to substitute each of these into its respective places. Okay, so that is the exercise that we left at the end of the last video. Let's move forward a bit. What we're going to do now is say, okay, there's a special, we'll call this a special case. And the special case is given a polynomial p of x, you're dividing by something of the form x minus c. Okay, so if you're dividing by, if your divisor is of this special form, x minus c, then you have certain specific things that happen. So first off, p of c, so this number is c, so c is some real number. C is a constant. And if you plug c into this polynomial, this actually equals r, the remainder. So let me explain why. Well, we know that in general, p of x is equal to d of x, the divisor, times the quotient plus the remainder. So in particular, we have x minus c here times q of x plus r of x. But this r of x, remember, this thing has degree 1. The d of x, this is x minus c, the polynomial x minus c, this thing is a degree 1 polynomial. We know that the degree of r of x has to be less than the degree of d of x. Well, d of x is x minus c. That means the degree of r of x is that's going to be less than 1. This degree has to be 0. Well, what is a degree 0 polynomial? Degree 0 polynomials are constants. Right? So for example, if I had r of x be 3, that's degree 0, because it's 3x to the 0. We mentioned that in the last video. So instead of r of x, we can just call it r. Let's just call, so we're going to label, let's call r of x just equal to r, because it's just a number. It's just some number. Okay, it's just a number. So what we have then is that p of x is equal to x minus c times whatever the quotient is plus some number r. And so now if you plug in x equals c, what do you get? You get p of c is equal to c minus c times q of c plus the number r, which is just 0 plus r, because c minus c, this is 0, and 0 times anything is 0, and hence p of c is just r. Okay, p of c is the remainder when you divide by x minus c. So this is actually a theorem. So let me just restate it. Let p of x be any polynomial, and d of x be x minus c. Then p of c is equal to r, where in general p of x as a function is x minus c times the quotient q of x plus r. Okay, so this is, I'll call this theorem 1. It's equal to the remainder. We'll do an example of this shortly. So let's actually do a quick example. So before we go to the next part. So an example here, well, let's take x squared. So p of x is equal to x squared plus 2x plus 1, and d of x is equal to x minus 2. Okay? So let's do long division here. X squared plus 2x plus 1, and we're dividing by x minus 2. What do we get? Well, the lead term divided, x squared divided by x is just x. So we get x squared minus 2x here. We subtract. We get 0, and then 2x plus 2x is 4x. Drop down the 1, we get plus 1. So we have plus 4 because the lead term here divided by this lead term, that's just 4. So plus 4, when we multiply the 4 by this guy, we get 4x minus 8. We subtract, we get 0 plus 9. So this is our remainder. This is r. This is q of x, and this is d of x. So what we have then is x squared plus 2x plus 1 is equal to x minus 2 times x plus 4 plus 9. So this is my p of x. And the question then is, what is p of 2? Well, what it claims is this equals r. In this case, that equals 9. And you can see that since you can see it in two ways. P of 2 you can plug in directly. You get 2 squared plus 2 times 2 plus 1, which is 9. That's method 1. Or we know here that p of x is x minus 2 times x plus 4 plus 9. Right, that's what we got from the division algorithm. So if I was to plug in 2, I would get 2 minus 2 times 2 plus 4 plus 9, which is 0 plus 9, which is 9. Okay, so this is an illustration of this particular theorem, that if you're dividing by x minus c here, then if you plug in c, so notice, by the way, c here is 2. C here is positive 2. It's not negative 2, it's positive 2. Okay, so just be a little careful about c. C is always the opposite of the sign that's present there. So c is not equal to negative 2. Okay, this is very important. It's a very common error. C is the opposite of the sign that is given in the d of x. Okay, let's do another example, and we're gonna see that there's something special about this example. So p of x is x cubed plus 3x squared minus 4x minus 12, and we're going to divide by x minus 2. So let's do this division. Well, if you divide lead term by lead term, you get x squared here. So we have x cubed. Let me erase these little underlines. So we have x cubed minus 2x squared. We subtract, we get 5x squared here. Let's drop down the next term, we get minus 4x. So here we get plus 5x. So we have 5x squared minus 10x. Subtract, we end up with 6x minus 12. Divide again lead term by lead term. 6x divided by x is 6. So we get 6x minus 12 exactly. And the remainder here is 0. So notice that our polynomial x cubed plus 3x squared minus 4x minus 12 is equal to x minus 2 times x squared plus 5x plus 6 plus the remainder 0. So notice a couple of things. Well, first off, since this is remainder 0, we just have that x cubed plus 3x squared minus 4x minus 12 is equal to x minus 2 times x squared plus 5x plus 6. So actually, so we have a couple of facts here. X minus 2 is a factor. You can factor it out of the polynomial p of x. Remember, this is our p of x right here. It's a factor of it. Second thing is, if you plug in the number 2, remember c here is 2, p of 2 is the remainder, which is 0. Right? This was r. And you can see that if you just plug in 2 here, you get 0. And so the fact that r was 0 means that exactly that x minus c, in this case, was a factor of p of x, and p of c is equal to 0. And that's the kind of corollary of the previous theorem, that when the remainder is 0, that x minus c is actually a factor of your polynomial. Okay, and you can see that visually right here. X minus 2 is a factor of this polynomial, and if you plug in 2, you actually get 0. Okay, so let's just write that as I'll call it a corollary. So the following are equivalent. So number 1 here. So the following statements are equivalent to each other. So you're given, it's the same situation. You're given p of x and d of x is x minus c. Okay, this is always going to be our assumption for the rest of this video. So when dividing p of x by d of x, which is x minus c, the remainder r of x is 0. If that's true, that's equivalent to saying x minus c is a factor of p of x, and that's equivalent to saying that p of c is 0. So if p of c is 0, what we say is c is a root of p of x, or c is, another way of saying it, c is a 0 of p of x. A 0, c is a 0 of p of x. What does that mean? That means exactly p of c is 0. Okay? So let me leave you here with a little exercise. And this one's, it's not too bad. So given p of x is equal to x cubed minus x squared plus 4x minus 4, and d of x is equal to x minus 1. So what I want you to do is show that r of x is equal to 0, i.e. x minus 1 is a factor of p of x, and that p of 1 is equal to 0. Obviously, if you just plug in 1 here into the p of x, you'll see that it's 0. But what I want you to do is use long division here. So do long division to actually show in another way that not only is p of 1 0, x minus 1 is a factor and the remainder is 0. So go ahead and do the long division here, and we'll start with this exercise at the beginning of the next video.